Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hakimi and I'm from Group 3 and I'm going to present about Task 1. So my group was going to present about project background, pillar table, flowchart, solution question 1 and question 2. So for the project background is signal to noise ratio compares the strength of the signal to the strength of noise. The most common way to express it is in decibels, or we call it dB. Signal to noise ratio was important because it shows how strong the signal is in comparison to the noise on the channel. The signal to ratio is 0 dB when the signal power equals to the noise power. The receiver is unable to differentiate between signal and noise. As a side note, the most common noise model that we discussed is AWGN, which means that noise is always introduced to the original signal and the receiver receives a signal that has been augmented with noise. Thank you.
Hello and Assalamualaikum. My name is Emirata binti Afrata from Group 3 of Electric Communications. So today I will explain about pillar table for my task 1. For the first fact, unit for all noise factor F and power gains A must be changed from it to ES or insert it to phase formula equation. For the idea, the value of gain for amplifier 1 and 2 must be changed to unit. Learning process, conversion of dB to absolute value. For the F, A is equal to 10 log 10 shift log 10 A divided by 10. For the second fact, the initial temperature must be in Kelvin. Initial temperature for chamber 1 must be changed from degrees Celsius to Kelvin. Conversion of degrees Celsius. For the X, Kelvin is equal to 3 Celsius plus 273 Kelvin. For the third fact, when 2 or more amplifiers are cascaded, the total noise factor is the accumulation of individual noise factors. The idea, noise factor contains a lot of information about noise communication system. The learning process is phase formula. The X is the formula of the phase, which is Ft equal to F1 plus F2 minus 1 divided by E1 plus F3 minus 1 divided by E1 times E2 plus Fn minus 1 divided by E1 times A2 plus the number of A plus and so on. The fourth fact, the minimum noise will be produced when amplifiers will each phase descending order of factor. Arrange the chamber based on the noise power factor from lower to higher. The learning process, calculation of noise power factor. The chamber was placed from lower to higher value by referring to its power factor. And the last one is the lower value of equivalent noise ratio, which is EE, the better the quality of a receiver. The idea, compare the noise factor of each chamber. The learning process is the noise factor formula, which is F equal to I plus TE divided by T. That's all for the pillar table. Thank you.
Assalamualaikum and hi, my name is Abdul Muiz bin Muhammad Nasir. My metric number is AE180006. Right, today I will continue to present about our flowchart of this project. So for this project, the first step is we will define the problem or criteria. So based on this project, we will define the complex problem of noise impairment in communication system, and we will also understanding the given receiver system design parameters, limitation, and the signal to noise ratio SNR calculation. So it is to solve the project question in this project. Right, after that, the second step is we will gathering all the information from this project question. So some of the important information that we are gathering are the noise effect SNR, the other factors considered, current available technology or method used to increase the system SNR. So Other than that, low or high complexity and cost of available solution. And the lastly is the equation used. After that, we will proceed to the brainstorming on multiple solutions. Either we use the technical or non-technical solution will be used in this to make calculation for this project. And then all possible solutions such as temperature, filter, amplifier, modulation, and others will be listed before we proceed to the solutions. The next step is we will make decision process to select the best solution. So it will meet the desired criteria in signal and noise level analysis. To get the best results, we will check the value of SNR to proceed to the next step. If the value of SNR is more than the maximum target, the previous step will be repeated with the different variables. If the value of SNR is less than the maximum value, the analysis results and discussion step will be proceed. So finally, the completion of report writing and video recording will be done and submitted to our lecturers for evaluations. So that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, my name is Amir Aiman bin Rozalani and my metric number is AE1800N44. Okay, so today I would like to present about our solution for the question 1. Okay, so we go to the specification first. Okay, we have specification of amplifier, and this amplifier device are portable. That means it can be relocated inside of the chamber, and we also have 3 chamber, and chamber are non-portable. That means cannot be relocated. Okay, and specification of amplifier, we have A1, we have 4 decibel. We already convert to the unitless. Okay, for dB we will get 2.512. For amplifier 2, 3.162, and amplifier 3 already in unitless, 20, because the calculation must in unitless. Okay, so for the specification of the chamber, okay, for the chamber 1 we have the initial temperature, we have 350, and the chamber 2 we have 25 Celsius, and we just convert to the Kelvin. Okay, and 298 Kelvin to 300 Kelvin, and the chamber 3 we have 295 Kelvin to 415 Kelvin. That means we can choose any of the temperature of the chamber. Okay, so we go to the step 1. Okay, the step 1 is we have the information given is signal power, which is PS, so equal to 5 watt, and the bandwidth is 400 megahertz, and the temperature of the sun we have 35 Celsius, and we just add 273 to convert into the Kelvin, and we also get 308 Kelvin. And how much the noise power? Okay, and the noise power we get from this formula. Okay, the 10 log power of 10, this is K. K, and this is bandwidth, and this is temperature of the sun, and we just divide by 1 milliwatt. Okay, this is negative 87.695 in decibel milliwatt. That means milliwatt decibel. Okay, so we convert to decibel milliwatt to the power of the milliwatt. Okay, so we get the power in milliwatt is 1.7 times 10 power of negative 9 in milliwatt. Okay, to get the power, to get the signal to noise ratio input, that is between the signals and noise power, signals and noise ratio. Okay, so we just signal power, just divide by noise power, and we will get 2941176.471 mega, okay, in unit less. Okay, so we go to the step 2. Okay, the step 2, we just find the value of the noise power, noise factor each of the chamber. Okay, for the chamber 1, we just select the minimum value of the temperature. Okay, for the chamber 1, it is only 350K, and the chamber 2, we just select 298 Kelvin, and the chamber 3, we just select 295 Kelvin, because to get the maximum value of the SNR, we must choose the lowest temperature of the chamber. Okay, the chamber or temperature. Okay, so the noise factor of the chamber 1, we obtain 2.207, and chamber 2 we get 2.028, and the chamber 3 is 2.017, and this is an arrangement of the chamber of the amplifier inside of the chamber. Okay, we have 1, 2, 3, 4, 5, 6 arrangement, which is A1, A2, A3, A1, A3, and 2, and the last one is A3, A2, and A1. Okay, at this part we must find the noise factor, the value of the noise factor. Okay, the formula is Ft equal to F1 plus this Ft2 minus 1 divided by amplifier 1 plus F3 minus 1 and divided by amplifier 1 times amplifier 2. Okay, and we also know about the SNR out, signal to ratio out, and this formula, signal to ratio out is inversely proportional to the noise factor. Okay, to get the maximum value of the signal to ratio output, we must find the minimum noise factor value. Okay, so at this arrangement we have sig. Okay, we just get this is the minimum value of the noise factor. Okay, and 2.094. okay, and that we selected arrangement that we selected is A3, A2, and A1 inside of the chamber 1, 2, and 3. Okay, and this we shown this calculation to get the value of Ft. Okay, and how we calculate the signal to ratio output. Okay, this SNR in, just divide by total noise factor of the arrangement A3, A2, A1 2.094, and we will get 1404573.291 mega. That's all from me for solution question 1. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Anishaira. I will continue to answer question number 2. The question is, without considering the mentioned condition and limitation, what could you propose to further enhance the output of SNR? Okay, to get the maximized value of SNR out, we must find the left value of noise factor based on the formula of SNR out. So basically, SNR out is inversely proportional to noise factor, or we call it as Ft. Okay, based on the data given, it has been given the gain for amplifier 1, amplifier 2, and amplifier 3, and then the minimum temperature for chamber 1, 2, and 3, and the maximum temperature for the 3 chamber. Okay, so as we have no data about the noise factor, so we have to calculate each noise factor for the temperature. Okay, firstly, we have to convert the gain for amplifier 1, 2, and 3 to become the absolute value. For amplifier 1, we have to change the 4 dB gain with anti-lock 4/10, and then we will get the absolute value for amplifier 1. We'll do the same step for amplifier 2, and then we get the 5 dB gain become 3.162 unit less. Okay, and then for all the minimum temperature for chamber 1, 2 and 3, we have to change it to Kelvin, and then the maximum temperature for chamber 1, 77 degrees Celsius, we have to change to Kelvin by adding with 273. To calculate the noise factor for each temperature, we have to use this formula, which is 1 plus equivalent noise factor temperature over environmental temperature, which is constant 290. Okay, and then we calculate the noise factor for F1, and then we calculate it, we get 2.207. For F2 we get 2.028, and then F3 we get 2.017. Okay. After that we have to randomly place the amplifier 1, 2 and 3 in the chamber. So we get for the minimum value, we get the less noise factor is when the place of the amplifier at A3, A2 and A1. Okay, and then we do the same step for maximum value of temperature. Okay, so basically the total noise factor, I use this formula, which is F1 plus F2 minus 1 over A1 plus A3, sorry, I mean F3 minus 1 over A1 times A2. So basically this is the formula that we use to get the total noise factor value. Okay, when we use the maximum value of temperature and we rearrange the amplifier, the least value for maximum temperature is 2.274, which is higher than when we use the minimum value of temperature. Thus we choose the minimum value of temperature at A3, A2 and A1 as the total noise factor, we put the value in SNR out formula, which is SNR out equal to SNR in over noise factor, total noise factor. So here we get the answer for question number 2. So that's all from me. Thank you.